Hello again, stat students, back here with another unit overview. This unit here is the normal distribution unit. So this is just an introduction unit to the normal curve. Um, Normal curve ends up being utilized in many of our units, but here is just the situation now where populations are already normal. That's relatively rare in the real world. You think about ACT, SAT scores are normally distributed because they're standardized, or with being standardized tests. Heights of fully grown individuals are pretty much normal. Um, and a handful of other situations, IQs in the real world that are already normal. And we're going to go right to the normal curve down here first. A couple things with the normal curve. So one thing to note here with the populations already being normal, in this unit, we're talking really about situations where n equals 1. In future units, we're going to talk about how n does not always have to be 1 and in fact needs to be much bigger than 1 in certain cases to ensure that we have a normal curve. Here in this unit, it's unique because it's always 1. And what will happen is we'll always get a sigma. Okay, so there's two different types of ways. When we talked about it on a previous unit, that one variable stats, we actually looked for S, which is a sample standard deviation. In this situation, we are given sigma. Okay, so we get a population standard deviation, or we're given everything else and we're solving for sigma. But this is a population standard deviation because we're talking about populations in this case and in this case specifically, that are already normal, or that are normal. So a couple things here. What you're going to see is if we take something like ACTs. So ACTs in the state of Minnesota might have a kind of a general relationship that maybe looks something like this, where the mean is about 25 and the standard deviation is maybe 3. And so it goes up and up by 3 each time for a standard deviation there, down by 3 each standard deviation here. And again, these lines then represent the standard deviation. So these are raw values here of ACT values. Now, you can take those raw values and actually apply this standardized score formula here, the Z formula, which takes your raw value and subtracts, in this case, we're saying the mean ACT here is 25. And so, for instance, if you have a ACT of 28, you are 3 above the mean. And if a standard deviation here is 3, then you are 1 standard deviation above the mean by being a 28. And so the other way of labeling these curves is by z-score. Z-score is always going to have a 0 at the mean, because that's 0 standard deviations from the mean. And then it would go 1, 2, 3 here, -1, -2, -3 down on the lower scores. This technically keeps going on, but as you can see here, 99.7% of the values in a population are within 3 standard deviations of the mean. So we don't talk much beyond 3 each way, but you could be 4 standard deviations. Some of the greatest hitters of all time in baseball had a batting average that was about 4 standard deviations above the mean batting average at their time, their era in Major League Baseball. So it happens. As you can see here, somebody who earns a 36 on the ACT is almost 4 standard deviations above the mean, 3 and 2/3 standard deviations above the mean. So let's just talk quickly about this breakdown. So these are all approximations here, the 68, 95, 99, 7. But what they are telling us here is roughly 34% of those in a population are going to be with between 0 and 1 standard deviation below the mean. Okay, so that would be right here. And about 34% will be between 0 and 1 standard deviation above the mean. And by 0, I mean at the mean to 1 standard deviation above the mean. So those are approximations, but about 34% are each direction there. And then within 2 standard deviations is 95% of the values in a population. So this is another 13.5% here and 13.5% here. And that represents that group that would be between 1 and 2 standard deviations on either side for each of those 13.5s. And then 99.7 is within 3 standard deviations. So there's another about 2.35% here on each side. And then finally, there's about 0.15% that's going to be outside of 3 standard deviations either way. This, again, approximations all the way through, but this is generally how a normal population is going to be distributed, which again, ACT, IQs, SAT, heights, and so forth. So what we would tend to do here is we would be either given a mu and a sigma, or given other values like a z-score here, and we'd be working with these populations and finding out some probabilities or some values that might put you at a certain spot on this curve. So the first type of problem that we see here is a question like, what's the probability that somebody has an ACT score of greater than 32? Now, keep in mind this curve is continuous, so there's really an infinite number of vertical slices in this curve. So whether we write it like greater than 32 or greater than or equal to 32 doesn't matter. It's going to be the same question either way, because it's not discrete. There is no difference really between 32 and 31.999999999. And again, that has to do with the infinite number of slices that we have in this curve. So what we do with that 32 then, which is a raw value, is we'd apply some algebra to it. And the algebra here would be the z-score formula. So we would take 32, we would subtract the mean, we would divide by the standard deviation, and find that the z-score for this person is approximately 2.33, or 7/3 in this case. So that z-score here on this curve would be somewhere around right here. And we want to know what the chances of being greater than that are, so we actually want to know this area to the right of it. Okay, and so we have gotten to the z-score, and now we are going to apply this calculator function. This used to have to be done with integration with calc-based stats, and now calculators allow us to kind of skip that element kindly. And so what we're going to do is we're going to look at this function, normal CDF, which is in second vars on your calculator, or distributions. And we are going to put in the lower bound of what we want and the upper bound of what we want. And so when you look at by what we want, we mean this blue shaded area here. So the normal CDF in this case has a lower bound of a z-score of 2.33 and an upper bound technically of infinity, but we know that this curve essentially has very little to no area, or at least very little area beyond 4 or 5 standard deviations out. So we just put some arbitrary big number there. So we have a normal CDF 2.33 to 99. Your calculator is able to actually use this without having to find the z-score. We don't talk about that much because the z-score is a valuable item in AP statistics. So normal CDF 2.33 to 99, and then that would give us the probability that somebody scores 32 or above on this ACT score, or greater than 32, depending on how you want to term it. But the way we wrote it there was greater than or equal to 32. So it'd be 32 or above, which is about 0.0099, or about 1% chance that they'd score above or greater than or equal to 32. So that's one way. Now you could have asked less than 32, in which case we'd be finding all the area to the left, and that would be a negative 99 to 2.33, which of course would be 1 minus that answer, or about 99%. Or we could even ask a between scenario. So we could ask what are the chances that they score between a 25 and a 32. And in that case, you'd find the z-score for both, and then you'd run a normal CDF from the lower z-score to the greater z-score, and you'd find that area in between. Okay, so you can have greater than, less than, or in between on the normal curve. And again, it's all about finding the area of that shaded region. And the overall area of the curve, it's important to note, is 1, representing 100% that you'd have be somewhere under the curve, and it's all in that probability scenario there. Now, the other type of problem that you see is actually going the other direction. So imagine the scenario where somebody says, what's the cutoff to be in the top 10% on the ACT? And so we look at this curve, and we have our normal curve, and the top 10% is up here, roughly there. And actually, we don't typically even shade that. We just would maybe have the cutoff here. So the top 10% cuts off right there, which of course is at the 90th percentile, since that all adds up to 1. Now, the reason this 90 becomes important is our calculator always works with area to the left. And so in this case, this inverse norm function, which as you can see, you go from percentile to using inverse norm, This is also in their second vars or distributions on your calculator. And if we run an inverse norm, when we run this, because your calculator is area to the left, we actually have to put in 0.9 here, even though the question was about being in the top 10%. So we just take 1 minus the 10 and always get area to the left. If it just asked being at the 90th percentile, then you naturally just use that 0.9 as is because it's already area to the left. So that gives us a z-score of about 1.28. Okay, so now we're in that middle part of this problem number 2 here. Okay, and now it says we got to run some algebra here. And this algebra is simply that we have now from this formula up top, we have the z-score. We don't have the x, we don't have the ACT that puts you in the top 10%. We do have the mean as 25 and we have the standard deviation as 3. And so now we're going to run some algebra here. And it's 1.28 multiplied by 3 on both sides, add the 25, and as it turns out, to be in the top 10%, somebody needs an ACT score of about 28.84. Now, because ACTs don't give you decimal answers, in this case, to be in the top 10%, you'd naturally need to be at 29 in this case with these numbers here. And not even if it was 28.2, you'd still have to round up to 29 because if you go down, now you're going to the part of the curve that's not in the top 10%. So you'd always have to round up here to be in the top 10%. So that would be the second type of problem there, where you go from percentile through z-score to raw value. Let's just break down in general what these curves kind of look like. The normal curve is the one that we see most often. Symmetric and normal. This is one we work with the most often, but it is important to note that not all curves are symmetric and normal like that. It could be symmetric but not normal. Like you see here, that's bimodal. That was referenced in the last unit where it has the two highest points here on that curve. Okay, skewed to the left. Okay, skewed to the left is where this is now dragging out to the left. And as you can see here, this notes the mode, which is the highest point on this curve, and then the median, and then the mean, and again, the mean gets pulled out the most because the mean is non-resistant. Okay, so those lowest values are having the most effect on the mean, these values that are dragging out way down here. The median doesn't get affected quite as much because the median is resistant, which is a topic from the single variable unit. Similarly, if it's skewed to the right, same sort of thing where the median gets pulled out a little, the mean gets pulled out a lot. Skewed to the right, we see a lot in economic sort of situations. So if you're talking about incomes or home values, a common one is salaries in professional sports. And we talk about the Twins when Joe Mauer was on the roster and making much more than any other player. They had a couple players making a lot of money, and then most of them made well under the mean. So the mean was about 4 million, and about 20 of their 25 players on their roster at the time were making under 4 million. So the mean was very much not at that 50th percentile like the median is. And what happens is the median is being that 50th percent is that 0.5 point, whereas the mean is actually the point where, like, if you were balancing this curve like a basketball on your finger, you'd balance it at the mean. So that idea of skewed versus symmetric here is important when you're talking about what statistics to use. And this is kind of a recap from last unit as well, where mean and standard deviation we like to use if it's symmetric. And that's why you'll see mean and standard deviation most often when you're working with a normal curve, because it works well with those curves. It's the best statistic to use in terms of the mean gives us a little more information than the median. Because we can figure out from the mean, if the mean salary is 4 million and there's 25 players, we would know that the overall team salary is 100 million in that situation. We wouldn't know that with the median if we were told that the median salary for the Twins was 1 million and they had 25 players. We wouldn't be able to figure out the total salary for all the players. So total sum, that is. And so the mean and the standard deviation are nice to have. Again, standard deviation is roughly kind of that average distance that a value is from the mean. And then if it's skewed, then we go back to using the median and IQR more so because they are resistant, so they don't get pulled heavily by these outlying values out here, so they can be a little better there. But big picture here, this is really about the normal curve. Again, in this situation, it's the a little more rare situation where it's already normal. Future units, we'll talk about what happens when it's not normal to begin with, and that's where the problems get a little more involved. So the formula that you saw here, the x minus mu over sigma, is kind of a starting point for us that we build off of moving forward. Thank you for listening. If you have any questions, as always, please make sure to ask, and we'll see you in the next unit.